And we're back from commercial. Here we go. All right, now let's get back to the action where we were just talking about RPMs, and RPM is an acronym that stands for revolutions per minute. All right. And you'll commonly see that associated with things that are spinning in real life. So if you see RPM, just say, oh yeah, that's right, it's revolutions per minute, got it. Okay, we're going to do it the same as we did in the front page. So let's see. So 200 revolutions per minute, that's the slowest a CD will go to be able to read. And they also can go faster as well, depending on what part of the disk you're on. So find the velocity of the outer edge in centimeters per second. We keep speaking about this outer edge here. Does it make a difference? What makes a difference? I mean, wouldn't the outer edge be going as fast as the inner edge? Wait a minute. Picture that as a line segment right here. If that line segment, let's say that line segment took 1 second to go all the way around. Doesn't the outside have to cover more ground in 1 second than this does? Because they're all going around in 1 second, right? So the outer edge is actually spinning the fastest of anything that's spinning, isn't it? Okay? If you go to the exact center, it's actually not spinning at all. It's kind of like standing at the North Pole. If you're at the North Pole, the Earth's not spinning that much. But if you're on the equator, you're going around really fast. Because it all has to go around in 24 hours, right? Okay. So the outer edge is moving the fastest because it's all moving together. Okay, this could be a frisbee spinning, it could be a CD, it could be anything. All right. Okay. So it does actually make a difference. All these problems are going to be the outer edge, every one of them. Okay. All right. So let's do this. Let's start off with what we always find first in a circular problem, which would be circumference. And the circumference here would be what? Let's see. Oh, it's d pi, isn't it? Right? Wouldn't that be 120 pi millimeters? Okay, there's my circumference. All right, let's write this as a fraction. How do you write 200 revolutions per minute as a fraction? 200 revolution, and then divided by 1 minute, right? Okay, so 200 revolutions every 1 minute. And of course, the word revolution I will replace with what? And 1 revolution is a circumference, and that is 120 pi. I'm going to put that right in there. Okay? Oh gosh, we have to multiply 200 times 120? Sheesh. I guess we'll have to multiply those together. Guess there's no shortcut. Okay? Well, watch this. First of all, it says centimeters per second. I've got minutes. If I want to go to seconds, what do I want to cancel out? Minutes should cancel, so I should put it where? On the top. But I want to introduce to the problem what? Okay, per second. And that's going to be 60 seconds equals 1 minute. Okay. Matter of fact, as we do all these, you can see, isn't this kind of like a distance over time, d over t? Okay, we're doing rate. Every time we're doing this, we're doing distance over time before we do the conversions. Okay. Now, one other little trick. There's going to be one of these on the test. It says millimeters, but we want centimeters. Okay. I will not make you memorize the entire metric scale. We'll only do a centimeter millimeter example because that's the most common, probably. So let's do that one. What do I want to cancel out here? Millimeters, so I should put it where? If you put it on the bottom, it will cancel, and on the top we will put, and which one goes into what? Do millimeters go into centimeters, or centimeters go into millimeters? Millimeters are the smaller one, so it's how many millimeters in a centimeter? Should be 10 per 1 centimeter. Okay? And it's the only measure conversion you'll need to know for this test. All right? So with all that, let's see if we can simplify and get a grand total here. Can we do it? Well, I got to multiply 200 times 120. Well, luckily for us, real-life CDs measure 120 for the diameter, and you have 60 seconds in a minute. How fortuitous. If we then choose a different size for CDs, that works out well for us. 60 goes into 120 how many times? 2. Oh, that's nice. Look at that. Okay. Most real-life stuff gives you wacky decimals, so we really lucked out here. All right. Oh, and 10 goes into 200 how many times? Nice. So this is 20 times that. And the only units I have left at this point are, look at the board, centimeters per second. Ah. Okay, so we have 20 times 2 is a grand total of 40 pi centimeters per second, and we got it.
I win.
Okay? 40 times roughly 3. Now you would think the CDs spin really, really fast. This is, of course, the slowest they go. But even this, if you convert this to miles per hour, it turns out to be 2 point something. Let's see, I did it. Yeah, 2.81 miles per hour. That's it. Because now, if you look at it spinning, it looks like it's fast. But if you picture a string coming out from it and driving down the street, it's actually not driving that fast if it was a car. So it's actually slower than you might think. But this is a lot faster than the tape cassette, which was like 0.17 miles per hour. Which is super slow. Okay? So there you go. There's your answer. So it's all about the conversions. All right, in example D, we have a Nissan 350Z. I would love to see the inside of one of those, but they're too expensive, so. So I got a picture off the internet, because I can't see inside one, so I got a picture off the internet. Okay? Wow, that's what the tachometer looks like. It's very nice. All right, so in this example, now you don't have to know.
Picture and put it on the internet.
No. Now, okay. All right. Now, what we have to do here is this, all right? You don't have to know a thing about cars to do this problem. We're looking for 1 revolution per 0.008 seconds. That's going to be important. And if we go faster than that, that little needle is going to get in the red line. And you don't want to be there too long. You'll mess up your engine. Okay? Now, we have, okay, let's see. Let's look for some other important information, all right? We've got something called stroke, which is like how far this crankshaft is moving inside the car. Oh, wait a minute. It says diameter. That's important. Okay? I don't know any of my cars, but hey, look. It says diameter. And it says the diameter is 3.2 inches. That's going to be important. Okay? That's how much this little part's moving. All right? So, let's see what else we have here. How fast are we going in feet per second? Okay. Well, let's do this first. What shall we find first? Let's find circumference, common theme of the day. All right? The circumference of this little part in the car that's moving around in your engine would be what? D pi, 3.2 pi in terms of inches. All right? There's your circumference. And according to this, now of course those little pieces in your engine are going really fast. All right? Super fast. Especially if you're going like 90 or 100, which you shouldn't be doing, of course. I heard these go that fast. I don't know. Anyways, I heard they go 130 sometimes, but I don't know. Okay, so no, I'm just saying, I don't know. So anyway, so
That's on tape.
cut that part out. Just cut that. I'm just saying, I don't know. That's what I'm saying. I don't. See, I said I don't know. Okay, so, but when you're going that fast, this thing's going around really super fast. If you get above this level, it's going faster than that. Okay, you're going a little too fast. All right, you need to shift gears or something. So here's what we'll do. 1 revolution per is what? Per is division, and then you put this amount there. And if we go faster than that, we're going to get into the red line. Uh-oh, okay. So that's like the maximum we want to go right there. And let's see. Oh, revolution. What's a revolution in this problem? It is the circumference.